Thank you for coming for this talk. In the next 35 minutes or so, we will be talking about how to hack mobile face recognition software without using fancy AI or deep learning techniques. So, my name is Wing Lau, and this work is the joint work with my PhD students, and we are from the Chinese University of Hong Kong. And here's the outline of our talk. Okay, so by now, I think most of us have used one of those face recognition technologies. For example, things like the Face ID from Apple iOS or the Face Unlock from Android. Okay, but the kind of the face recognition and interactive liveness detection software that we are going to talk about in the next 30 minutes or so is a different kind of animal. For one, they are pure software-based solution running at the application layer. This is in contrast to those iOS Face ID, which rely on specialized hardware support on the devices. Okay, and also the kind of the face recognition software that we are talking about, usually they are provided by either big platform like Tencent, Alibaba, Baidu, or other face recognition software service provider like SenseTime or Marvell or FaceTag. Okay? And since they do not rely on specialized hardware like the 3D camera in your iPhone, okay, they can run on all kinds of mobile platforms, and that's the advantage. But on that hand, since there's no specialized hardware support, in order for it to get a secure behavior, actually, most of the time, they will rely on collaboration from the back end of the cloud. In particular, after you capture your picture or your video, at one point, they will need to ship back to the cloud for the face recognition. Okay? So for these kind of technologies, the usual applications go beyond just a convenient login. In fact, I will arguably, they are more frequently used for so-called electronic know your customer application. Okay? In those applications, eKYC, what it did is that during the opening of some account, they will want to use this face recognition technology to verify the authenticity of the user to make sure that they are a true person instead of just some criminal using stolen credential to open fake accounts. Okay, in terms of the use case, these days we have using this kind of a technology to open a new bank account or open an account for crypto wallet, or open a new profile in a dating app, or open a new account in a social media, okay? Or even doing driver registration for car ride services, something similar to Uber in the US. So in those cases, there is strong incentive for criminals to create large amount of fake accounts, okay, for bad purpose. So if there's a need, there is a will, there's a market. You can find in the black market, actually, a total solution, one in all, is being provided. Okay? In those cases, you can just, with a small amount of money, to acquire photos of ID card or passport together with high-quality headshots of the victim with different angle. Okay? And then, in addition, tutorial and software to teach the user, namely that the hacker, how to edit the picture, modify the picture so that they can fool the face recognition software. And some of those actually also come with just a mobile phone with customized ROM, okay, to bypass this face recognition SDK. So in fact, there have been reported cases that people use this kind of bypassing technique, okay, to create fake bank accounts, probably maybe for money laundering or some other not so good purpose. And also, there are people that use it to create fake accounts for tax evasion. Okay, so in that sense, the threat is real. And in the academic research community, actually there has been quite a lot of work talking about how to defeat those face recognition software. And probably the one that get most of the media attention will be deepfake, which use deep learning AI technique to generate very realistic video to be fed into those mobile face recognition software to fool them. There are also other attacks which use so-called the presentation attacks, which use specialized masks or specially designed glasses to be worn by the attacker, okay, so as to bypass those face recognition attacks. And in contrast, actually, there's relatively few work which look at the system architecture, the protocol, design, and implementation of the face recognition software, okay, which is the theme of our work. And in fact, if you look at it, to the best of our knowledge, the most related work along this line, it is the recent work appeared a couple of months ago from IEEE S&P 2023, okay, that also looking at this kind of architecture, kind of attack. That work is a parallel and independent work of ours, okay, and it actually appeared after we submit our work to Black Hat. And the emphasis is a bit different. For us, we are emphasis on the attack side, really talking about the details of how to hack the software, how to exploit it so that we can bypass those face recognition software. Okay, so now let's take a look, give a high-level view of how does those face recognition SDK work. Usually, it consists of 3 phases. In the first phase, it's a simple one. Basically, the camera is activated and then trying to detect a face and make sure that the face of the subject is located in the proper location. Okay, once that's done, then a liveness detection algorithm will be run. The purpose of it is to make sure whatever the person appears in the picture, it is a real person, rather than just a display from another screen or from a printed picture. And once that's passed, then it comes to the third phase, where the actual face that is acquired, okay, will be sent to compare with either authority picture from an authorized database, from a government database, or in some other cases is to compare it from a picture that is extracted from a scanned government photo ID. So these are the 3 phases of action. So in terms of the liveness detection, actually there are different ways to conduct the liveness detection to make sure that whoever in the picture is a real person. The more rudimentary, simple way, so-called the static image liveness detection, all it did is that it just take one static photo and then using some machine learning algorithm to trying to identify whether it is a photo taken from a print or a display of screen, which you can see that may not be that sophisticated. So for the more sophisticated liveness detection, supposedly more secure one, they will require some interactions between the user and the mobile software. Basically, the mobile software will instruct the user either to conduct some prescribed motion, moving your head, or opening your mouth, or blinking your eyes, or in some other cases, to recite some phrase or numbers. Also, here, what we see is there's also something like so-called the flashing mechanism. So the mobile software will flash different lights to the subject and then receive whether the reflection show in the camera according to the flashing particular color of the light. Okay? And there's also another kind so-called, there actually the user is not required to do too many movement. Just stand there and then based on the subtle movement that more or less cannot be controlled by us, okay, to do it. So with that one, actually, we may think that they have put in a lot of effort to do liveness detection, okay? So, but on the other hand, it turns out it is not as secure as you would think. So let's take a look at the demo to see how we can bypass.
This demonstration shows an identity spoofing attack. Great. This is an app using face identification for bank account verification. The left screen shows a normal app as a reference. The right side is an attacker-controlled device launching the attack. Let's keep an eye on their differences. Now, we're starting the face recognition process. The app is using a mainstream SDK. The first step is face detection. This usually runs on your phone locally. It's just for triggering further face processing. So, there's not much protection, even if photo works. The next and most important step is liveness detection. The purpose is to check whether it's a real person. You can see the app is asking us to blink and nod our head. A photo may pass the blink detection, but not nodding. For the right screen with attack running, we can see the whole liveness detection passed. The final screen shows that our fake identity is accepted by the system on the right, but rejected on the left. In the background, I actually submit my own photo, so the my identity is verified. But attacker can use any victim's photo. Trump is not the victim here. His photo is only used to trigger face detection.
So in the previous video, we successfully bypassed the liveness detection and presented another person's image for face matching. How's that even possible? Here comes the technical part. So this is the architecture of a face recognition process. Usually one of the three alternative architectures is used. A pure local mode, where both the liveness detection and the face comparison are conducted on device. A local cloud mixed mode, it is the most popular in mobile apps. There's an on-device liveness detection, a cloud-based face comparison, and an optional second layer liveness detection in the cloud in between. The third architecture is probably the most secure one because it is called a pure cloud architecture. Basically, the Face SDK is just like an interface guiding the user through the process, but in fact, both liveness and face comparison are conducted in the cloud. We say that the third one is most secure because just keep in mind that any operation performed on the client side cannot be trusted. Because under our threat model, an attacker can have total control of his own mobile device, like a rooted phone. So here we are actually considering an important security usability trade-offs. That's why we have these three architectures. The third one, the pure cloud mode, is the most secure, but you're actually sacrificing the user experience. Because it solely depends on the cloud to perform the liveness detection. You have to upload the entire raw video clip of liveness to the cloud. And that may bring a burden to the cellular network. Or let's say, if only one of the three actions in the interactive liveness detection fails to meet the threshold, maybe the user needs to start all over again, start everything all over again, so that may irritate the user. So here's a more detailed step-by-step workflow of how it works. In some SDKs, the app's code may first query the face cloud to initiate a face recognition session. Some configurations are returned. The configurations include, let's say, the passing threshold of the machine learning models of liveness detection, and also the action sequences that are used for a user to spin his head or open his mouth. These are the action sequences. These configurations are used to initiate this SDK. The camera is streamed in, the liveness detection is conducted on device, and the liveness result is finally returned, passed back to the face cloud. The result data may include the raw video, but also it may only be some of the frames of the liveness video capture. There could be a secondary liveness in the cloud, and finally, we have this face comparison phase. Again, the reference photo may come from the app server or may come from another query to the authority database. So as you can see, we are actually talking about a multi-party communication channel. And based on that previous trade-off we have, there are multiple implementation choices. There are even more choices include, for example, for this SDK, is the business logic written in Java or written in native code? And the code and the machine learning models may also be packed or obfuscated. The configurations may be fetched from the cloud, or it could be generated or even hard-coded into the software's code. Some SDKs may also conduct some environment check-in, just to make sure that you're not running on a modified device. There will be something like anti-hooking, anti-root, or anti-debugging. As we've discussed earlier, there are 3 kinds of liveness. The pure cloud architecture is the most secure. And in terms of the liveness detection result, usually just returning this plain text result on device is not recommended because it'll be too easy for an attacker to replace and just forge the result. So most SDKs would encrypt or sign the plain text result and decrypt it on the face cloud. But for some apps, they may rather decrypt it on their own servers, so some SDKs would optionally also return this plain text result. So here's a reminder, a concise reminder of our attack setup. As an attacker, we own the victim's photos in the device under his own control, his full control. Our goal is, of course, to spoof the face recognition and identify ourselves or identify the attacker as the victim. The general attack method is to bypass and deceive liveness and to upload the victim's video or the victim's photo for face matching. In terms of attackers' capabilities, we usually only consider low-cost attacks here. So first, we won't consider if the reverse engineering is too demanding. We usually assume that the attacker can unpack, can hook, and deobfuscate the Java code. And again, we don't assume that we have any of those AI toolkits to do a deepfake or adversarial attacks. There could be also other sophisticated protections, such as emulator detections or a secondary image-based liveness, but they does not apply in our scenario because we are using a real device and we actually have the raw original image file of a victim. What makes our model, our threat model, actually practical is some more fundamental pitfalls in the system design or implementation of the face recognition protocol. So the general idea is that although we cannot attack the liveness detection core AI algorithm, we can attack the pre-processing part and the post-processing part. So for example, this is the initialization stage of a liveness detection. An attacker can just modify the action numbers, say from 3 to 1, or even an empty set, or just lower the threshold of the passing threshold of the machine learning model from 0.9 to 0.1. Yeah, so that's pretty easy. And if the action sequences are generated on device, I can just control the next action. So everything will be predictable at the attacker's will. Of course, the more secure way to handle this kind of situation is attaching all of these configurations to a cloud-based session so that the session is not forgeable or being able to tamper with. Another track of pitfalls occurs when the Face SDK is passing the local liveness detection result to the app server or to the face cloud. We call it the result passing phase. So this process is particularly crucial because we are not only uploading the result or liveness score, but also we are uploading those frames of the video we captured earlier for the face matching. So our attacks are also based on these ideas. What's shown here is the most straightforward case where there's no protection at all. So there's no encryption, no signing. Of course, as an attacker, we can replace the result, to replace the liveness score to 0.9 so that it will be higher than the passing threshold, or just replace the image from the attacker to the victims to pass the face matching. So this attack is easier than easy. A more secure design pattern we observed is that some SDK would encrypt or sign the images so that here, what is being passed here is already encrypted. And the SDKs would put those core business logic in the native code and heavily obfuscate it. And it is the face cloud who is decrypting and comparing the encrypted messages, images, and then returning the result back to the app server. This is a secure way to handle this, but we observe this pitfall. So some SDKs would return a non-encrypted, a plain text version of the image along with the encrypted one. And the app server, some app servers just don't want to, just want to do it in single shot. He doesn't want to query the face cloud again. So he would only grab this plain text version and then do the comparison. So to launch an attack, it'll be pretty much the same as the previous one, just by replacing this image suffices. This plain text image is already suffices. So the final pitfall here also falls in this result passing phase. The secure way for an SDK to encrypt is to first bind the bind the result, the liveness result, and the image all together before passing it to an encryption or signing algorithm. But some apps would or some SDKs would encrypt it separately so that you can substitute one of them and the things will go wrong. For example, here we can use the encrypted success message from one face session and then use another encrypted image of the victim. Combine it all together to pass the identity proof. This we call it a malleability attack, just to refer to the same concept in cryptography. There are also some other cliche mistakes like saving the file in an insecure location, in a public location, or that there are some SDKs that are not doing the UI hijacking protection. We further conducted an empirical study. So we analyzed 18 face recognition SDKs in the market and identified 11 of them have insecure design or implementation. There are some catastrophic cases, as shown here. For example, if the thresholds, theta, and the action sequences, A, are all configurable and not bound to a cloud session, or if the liveness results are just replaceable by some plain text message or images. So these actually coincide with our pitfalls that we discussed earlier. So there are also some other less secure design. For example, if you're conducting or an app or an SDK is conducting the environment checking purely in Java code, it will be easily bypassable. There are also some good practices, such as always do a second check on the cloud. But the point I want to make here is that a good practice does not imply 100% security, because we still have that security usability trade-off. So the thing we want to emphasize here is that an SDK may even sacrifice more security only because of these design implementation flaws without bringing them any other real benefits in usabilities. We also conducted a measurement study to see how many number of the apps are actually using those face recognition SDKs. We collected the stable fingerprints, and here are our results. We found that the financial apps are the primary adopters of face SDKs, accounting for 25% of all those SDKs in our analysis. So most of these apps are actually using those insecure SDKs. As you can see, the digital wallets here with the banking apps here. There are some SDKs highlighted in red. They're all the insecure SDKs we talked about earlier. So now I'll pass the presentation to our remote speaker.
Okay, now I believe you have a big picture of what kind of vulnerabilities are those SDK tends to have, and also you know what an attack looks like. Now let's look at some concrete example app, especially for those of you who prefer to read code. This particular app tries to use some banking service, and the bank also provides some integration library for mobile apps to use. And because the app also needs to identify who the user is, it relies on some face recognition service, which also provides its own SDK. So the banking SDK just integrates the face SDK. And when the app includes the bank SDK, essentially it also includes the face recognition SDK inside. So as an attacker, to investigate this particular app and to launch the attack, generally there are three phases. The first phase is reconnaissance. It is to look into the app to see whether it is packed and which face recognition SDK does it use. And then he needs to analyze the SDK or the app code to identify the vulnerability and to know, well, what kind of, to plan ahead, what kind of attack or exploitation he want to perform. And finally, he launched the attack. Now let's look into detail of each step. First, after looking at the app, the first thing is to try to decompile it. The left-hand side screenshot shows what will attacker see if he try to decompile this particular app. You can see that there's a lot of nonsense package name and nonsense code inside. This tells us this app is packed by some of those popular commercial packers. And if you're lucky, you can directly find some of those open source tools to try to unpack the app. But the packers, those commercial packers, also upgrade frequently to defeat those known unpacking technology. So one trick we use a lot is to find very old version of the app. And because those old versions, they also use outdated packers or even non-packs. If you want to know more about the commercial packer ecosystem, you can read the paper listed here. So after we successfully unpack the app, this is how it looks like after we do the decompilation. We can identify some common well-known names, well-known libraries, like the OKHTTP3. But in some other times, it is very difficult or impossible for you to unpack the app. But you can still launch the attack. If you know where the vulnerability is, you can do the booking, right? So how can you analyze where the vulnerability is? You can just go to the SDK website and download the SDK and read the SDK code, because the SDK library itself usually is not packed. But one challenge we face is that many SDK providers, they only provide the SDK to verified enterprise developers. But we also find some interesting case, like in this case, this SDK, the download permission control is only implemented in the browser client side. So it's just like locking your bike without actually lock it. There's also other means, like we can search the package name in GitHub, and maybe some developer upload their app source code with that particular SDK. And also we can look at, with that, the outdated version of the app, which have no packing, so we can extract the SDK outside. And also it would be very helpful if we can read the SDK's official documents, developer documents, because usually their logo diagram, list of APIs help us to understand the SDK code when we do the reverse engineering. So now we have the SDK code. First thing we want to do is just to decompile and read the code. And in this particular case, we quickly identify there's some interesting things, like there are some hard-coded thresholds. Like showing in the code snippet here is a threshold that controls the hack detection confidence level. If we lower this value imagine if we lower the value from 0.95 to 0.0, then it effectively just disable the so-called hack detection, which would help the SDK to detect any kind of image modification or forged video. And also there are some other thresholds, like some threshold to control how the user should turn his head. Like the user is expected to turn his head 90 degrees. But after attacker to lower that threshold, maybe the user don't need to move his head. The liveness detection can still pass. Another very important function we found inside SDK is that it has some function allow you to configure the motion or action sequence. So by simply write some freedom booking code, we can replace the input specified list of motion. Usually it's just blink or mouse opening, shake your head. The attacker just can replace the configuration into an empty list of motions. By doing that, he may be able to turn the interactive liveness detection into static or even no liveness detection. So previous blocks are inside the initialization phase of the SDK. Now let's look at the more interesting, more important result passing phase of the SDK. Here we can see the SDK have the one interface or one callback called onComplete, which provide some raw byte, which is actually encrypted liveness detection result data. And also there are some list of image frames, which in raw image formats. Supposedly, the app should upload only the encrypted data to the Face SDK cloud server for decryption and further detection. However, remember the banking SDK, banking integration library, which help the user to integrate the Face SDK. When that particular integration library implement this onComplete logic, it totally ignores the encrypted results, but only fetch the raw image and do another round of encryption by itself. However, this kind of encryption is far less secure than the original encryption done inside the Face SDK. So in this case, who should we blame? First, of course, the banking integration library have a very poor security implementation. And also, the Face SDK, the face recognition SDK, is also to blame because it leaves the insecure option to app developer. And also, we know that it has those kind of hard-coded stressors, which also make it less secure. So now the attacker want to do the actual exploitation. He chooses to use hooking to do that. However, usually for those financial apps, you first need to bypass all those kind of anti-hooking or anti-debugging detection. Luckily, there's a lot of resources or tools available online. And after you're able to hook the target app, usually you'll find another challenge. You cannot identify the original, like the onComplete method you read in the SDK code in the app. Because when the developer compile the app, there's an option to do simple obfuscation, which just like name stripping. All of the meaningful method names are removed and replaced by those A, B, C, D, E. So how can you map those meaningless function back to the meaningful function inside the SDK? It's also not difficult, right? Just look at the data types. You know that if you know that your target method returns like the image bytes, then you expect to see some byte type of data in the argument list. So with this idea, we actually built a very simple framework in Frida that help us to reliably hook the obfuscated codes by matching those data type and return type. After we're being able to hook the target method inside the app, we can actually launch the data replacement attack. But first, we need to know the exact formats of the data the app expects. So first thing, we hook on the result returning function and dump the data to the SD card, and we pull that data maybe the attacker can pull the data to his computer for further inspection. And he can know the exact size or orientation of the returned image, and then he will crop the victim's image into the exact same format. Then he will place the victim's image back to successfully launch the attack. But sometimes the attacker may find that the return data after the liveness detection is encrypted. But keep in mind, as an attacker, you should keep in mind that all those kind of encryption can only be done in the app side, client side. So fundamentally, however sophisticated the encryption is, fundamentally it's the same. It doesn't add another layer of security. So there are some real examples of apps that only hard-coded the encryption key in the Java code. So if you can just decompile Java, you can easily locate those encryption keys. But in some other cases, it may require more efforts to actually reverse engineering the native library to identify which kind of encryption algorithm does the SDK use and try to recover the secret key. And by now, we introduced most of the important techniques used by the attacker needed to launch the attack. And you can see that nothing is very difficult, right? So this whole attack is very kind of simple. And we're not trying to teach you how to do actual attack, but we're trying to raise the concern and awareness of how insecure those face recognition services mobile apps are. Now, I will pass it back to our on-site speaker to give you a conclusion. Okay, now I believe you have a...
Okay, so that's the details about how can we hack. So what are the key takeaways? First is that even in this AI era, actually, sometimes instead of just worrying about those deepfake, very fancy attack, we need to be back to the basic. Make sure our system architecture, the protocol design, and implementation are properly done. Secondly, is that even if you are actively avoid using those face recognition technology or software, sometimes you will still become a victim because all it takes is to get for the attacker to steal your credential and then use it with this kind of hacking technique to open account on your behalf. So you will become one of those fake bots. Okay? And lastly, it also raised the need to have standardization on this kind of local cloud-based operation of face recognition applications or services. Okay? Say, for example, is it really secure enough without specialized hardware or hardware attestation? Those are the questions that we should keep in mind. Thanks a lot for attending, and we have time to take a few questions.